Another definition that's going to be helpful for us to have is this notion of a proper subset. Notice that earlier we've been using the subset, the is a subset of symbol, and it reminds us a lot of the less than or equal to symbol. But what would be a strict version? In other words, what symbol would go with strictly less than? And the answer to that is the proper subset symbol, is a proper subset of. And there's a lot of different versions of it, as you can see here. So some versions are the ones you see here. A is a subset of B. A is a proper subset of B. A is a proper subset of B. A is a proper subset of B. So there's different notations for the same idea. So then what does this mean? Well, we say that A is a proper subset of B if A is a subset of B and A isn't actually equal to B. Before now, all of the examples where we were saying A is a subset of B, technically A could have equaled B. None of the examples had that situation, but it is technically possible. That's why we make a distinction between just saying something is a subset of something and something is a proper subset of something. Symbolically, the way we would represent this is if A is a proper subset of B if and only if A is a subset of B and A is not actually equal to B. So how do we know that A is not equal to B and A is a subset of B? Well, another way to think about that is there exists an element in the universal set that's in B but not in A. Here's an example of what proper subset would look like. We have the set A, which is a subset of B, in this case not equal to B, because the two circles would actually overlap completely. And the way we can tell in terms of a proof is finding an element that's in B but not in A. Let's look at a quick example. The interval 0, 5 is definitely a proper subset of the real numbers because we don't have all the real numbers here in this set. There's a lot of them missing. In fact, these major sets that we've talked about before have this proper subset relationship. And then there's this connection with inequality symbols as well. Okay, this also has the transitive property, which is very similar to what we argued earlier in a previous part of this lesson. So the question for you to answer is true or false? Is the interval 3, 4, the open interval 3, 4, a proper subset of the closed interval 3, 4? What about the open interval 3, 4 being a proper subset of the half open, half closed interval 3, 4? Something to think about. Give that a try and then come back. Here's some fun little facts about sets and the empty set. The empty set is always a subset of any set you want, and every subset is a subset of itself. Okay, so remember what we were saying when we say is a subset of, we are including the possibility that A equals A. So we're not saying proper subset here. Okay. The important thing to note about this theorem is this part right here. This is a very useful idea. if you're trying to show using the definition of a subset that the empty set is a subset of A, what you're going to have to show is that if X is in the empty set, then X is in A. Now that should seem weird immediately because nothing is in the empty set. But what you can take from that is the fact that when you say X is in the empty set, that's automatically going to always be a false statement. And notice we have an implication and the premise of it is false. So what does that say about the whole implication? What is its truth value? If you said true, you're right. Okay, so we can prove that this implication is true by using the fact that X is in the empty set is always false. So that's a very helpful tip. We're using our logic knowledge to help us prove things that make sense to us, but we just don't know how to prove them rigorously. Okay, so looking at this example, we have empty set is an element of the empty set. Well, the empty set doesn't have any elements in it, so there's nothing that could be an element of the empty set. So this is definitely false. Is 1 a subset of the set containing 1? Definitely not, because, well, 1 isn't a set. The only way something can be a subset of another set is if that thing is itself a set. 1 is not a set. This statement doesn't make any sense. Now this last one is actually true because the set here written on the right is a set that contains the empty set as an element, which means this set has something in it and that thing is the empty set. So to say that the empty set is an element of the set containing the empty set is actually a true statement. And if you want to compare what I just explained with the solution, here it is. You can pause, take a read, or if what I said is good enough, you can go ahead and move on. Okay. One more thing before the next part. You should now try this on your own. Determine the truth values of all of these 3 expressions. Okay, you're really testing your ability to properly process the syntax of sets and the relationships among sets. Again, as mentioned earlier, we are skipping power sets in this class. I've only taken the summary and review of the parts of this section that we actually covered. These have the definitions that we talked about and these formal symbolic representations of these definitions, and some proof techniques involving starting with an arbitrary element in the set that you are starting with, and then showing somehow, using definitions, using properties that these elements have to have by being in a certain set, that they also have to belong to the next set. In other words, this is the subset definition. Remember that the empty set is a subset of any set, and any set is a subset of itself. But don't forget the definition of proper subset. It's definitely not the case that a set is a proper subset of itself. That's definitely not true. Quick look ahead. Next section will be talking about unions and intersections and other operations that you can do on sets. And it will turn out that a lot of the proofs involving these will yield some properties that are actually exactly the same in a lot of ways as the properties that we talked about in chapter 2.